we have been obliged to accept is that this kind of phase separation is not homogeneous, is not randomly distributed, but is more complex. This is the uncorrugated material. These are completely corrugated material. You have this happen in some particular case where you have patches of corrugated material and patch of uncorrugated material. Again, is a property of the complex system that want to frame modules. The modules are made by patch of lattice striped material and patch with nothing. The size of these stripes from this small angle scattering were of the size of nanometers, and there was a lot of impossibility for with techniques to see this kind of lattice non-homogeneity, lattice granularity, what Crazy describes as metal granularity. So we have metals and metal grains, the phase separation of different metals and with different size. And what there was what was very pleasant to see, there was also in the other, also in the binary compound, like magnesium dibride, like noble titanium alloys, and also with A15 materials, is it the same? We have different patches. We have a granular superconductivity. The granular superconductivity has been seen by Rogatis, Panagopoulos, in Anton Stonsson, recently, when you are, and also by the works of Kuzmartsev that has shown this exactly this phase separation of modules of polarons, not just a one polaron, but a group of polarons, a collective. And this is it's quite a generic behavior. How much? So this is the introduction of all the work that now we understand that IPC superconductivity appears not in the homogeneous disorder, not in the crystalline stripes, but in something, bubbles of parts. This was made for iron, arsenide materials, but now we can show every new data that is exactly the same as the ICO material. We're just measuring now ICO, and we have to arrive at the same picture of this one. So where this happen? The maximum this here is covered here, in this case. What happened when we decrease from the normal phase to superconducting phase? We have a network of phase coherent superconductors that percolate through the sample. This is what we have to derive from all these works. In order to make visible what is not visible, that is the topic of experimental physics. We just invented different techniques. So the x-axis was made, the polarized x-axis is very long k vector. So each technique you see, there is an effort to make a new experimental method to see something that you don't see. And if you, we have been using this last 3-4 years, a nano X-ray diffraction. Because nano X-ray diffraction is allow us to see in each module that you have a long-range order, the formation of paths of different striped bubbles. Because each striped bubbles will have a superlattice peak, will have a diffuse scattering peak. So I can see the different paths by going point by point with X-ray diffraction. So I have to go to have an X-ray beam and to go here, and then I see X-ray diffraction because of the lattice organization. Then I go here, I don't see nothing. Then I go here, I see something else. So I need a method that mixes K-space and real space. And this is the biggest direction where physics is going now. So not imagine that we make an experiment looking to the K-space. These are not space evolution your information in the K-space is not relevant. But what you will see in this case, you will see a small diffuse beam. But if you have a nano beam, then here you see a diffuse beam, but you don't see here. So you have to imagine the order, not imagine the material or the density. So we focused first on another source of lattice inhomogeneity that has been called extrinsic inhomogeneity, that due to the fact that all these pentanary compounds, you have to put also dopants. And when you put dopants, you have no fantasy, you think they are homogeneously distributed. But we know that this is not possible, because if the system has tendency to formate modules, also the dopants will formate modules. And so one way to see this kind of, we call this lateral inhomogeneity. When Boswich say, I have a superconductor with a single layer. What about lateral inhomogeneity? How is the gap here, here, here? And then STM already told us, you have a gap of 80 millib, a gap of 30 millib, a gap of 20 millib, so the system is not homogeneous. It's a granular superconductor. So let us look to oxygen and dopants. Why oxygen? First, because all the ITC superconductors have interstitial oxygen, and it's a common feature if you look to the first slide. And it's mobile, so you can treat with thermal treatments. You can make them completely disordered, you can play completely ordered, and you can follow with the heat treatments that Kramer started in 1992, presented the first phase evaluation in a Styles conference in Asia, that you change temperature, you can organize oxygens interstitially in different ways. But at that time we didn't know in which way. Now we went with X-ray to see how the X-ray gets self-organized. And then we have seen that we get beautiful X-ray diffraction peak due to the patches where ordered oxygen are perfectly ordered in 3D. Nothing to do with the Emery straps. These are oxygen ordered not in 2D, but in 3D, in plane A, B, C, I. And these are really a model. But this model, we can go now point by point, and this is the measure in 2010. We can go point by point, and that's what we see. In this point, no order at all. No superlattice split. Then we go to this point, huge superlattice split. We can detect without any scale. It's merely become a percentage of the main reflection. And then you have all the intermediate distribution. What does it mean? It means that you have a scale-free distribution. These are the patch where you have the order. This is the patch where you have complete order. No satellite. So look like a perfect satellite. This is a sample with 40 Kelvin by heat treatment. This is a sample with 17 Kelvin heat treatment. The same sample. Different heat treatments, different patches. One 17, one 40. So what we see now is that this kind of patch, if you plot the intensity of the diffraction, which is the volume of the order, then the volume of the order scale with the power law distribution with a cutoff. Why a cutoff? Because it's impossible, it's infinite size of the grains. So it's fundamental that it should be a cutoff. And as you go from 40 Kelvin to 16 Kelvin, the cutoff goes down. When you go to 60 Kelvin, to reach nearly a Gaussian distribution, the cutoff is very large. Then you can normalize the two. You see the cutoff is very large, it's normalized to the cutoff. And when it's quoting not power law, this goes down. Also the function, correlation function, you can see that a patch of ordered oxygen is correlated with another one. And we can characterize also and you can see that you can reach up to 100 micron correlation length. If you go to the other section nearby, where they put exactly in parallel to that, you will see granular superconductor, you can see case where this can happen. So the idea of what it is you have calculating satellite grains, what to strive material, because oxygen now is ordered, you can electronic structure is completely different. You have a different Fermi surface, because the oxygen is ordered, and with the album, we are calculating the Fermi surface completely disordered. You have a small electron pocket, you have a pseudo gaps due to the orbiting and so on, and then you have these ordered ones. And this can be also a result of the other phase separation on the copper between two metals. And this is the work that Google is going on. When you have a different electronic components, then you can have, like with the work with the Kuzmas, you can have a phase separation in the other module that is in contact with the oxygen. And they should go together. When we are in this situation, it's we start to look to the history of IPC superconductivity. And then I met Professor Maple here and at the coffee break, and I told him, when we found this page, we said, okay, if we put a little bit of light in this network, then it will be dramatic effects, because it will be some long-term effects. And then we went to see all the papers, by Golden used paper by Eager, Maple, and others, and in the early times, and we found perfect agreement. So as you make illumination, you have a threshold, because you need some intensity. If you put a little perturbation adding up, you have a critical threshold. When this light fast increases the critical dose, the critical fluence, then you have a fantastic effect. Why? Because it's very little energy to change the network of the old material. This was one of the topics of the COMEX project we organized with the Rogalis. And actually that's what you see. You illuminate what we developed is the idea of using as illumination X-rays in such a way that the penetration depth of the probe X-ray diffraction is the same as the palm. And that is we can map to optical situation. And then we studied all we took a piece where there was completely disordered oxygen by radical quench, and then we illuminated, now without thermal treatment, but only illumination. And then we see, you see the same, after some time, you see this going up. This took about 5 years or 6 years to make this experiment, because in order to find exactly calibration of for the user effect that you can measure in a time of 1 or 2 days, there's a beam time in the single radiation. Took about 10 years, I think. But the discovery was made, I think I remember, was made by my daughter, Bianconi, that was coming to make an experiment in Trieste, and they were in night, we went to a fish restaurant, came back, and the diffraction pattern was completely different. And this is a positive user effect. You see this speaker. When we go up before dinner or something like that, when we got was a fish restaurant in Trieste, in Pescatore, that is a very good restaurant on the Marco. And then coming back from Marco, we have also very good white wine, and we were hygienist and a technician. And we get back, put up the data, and the screen was completely different.
Must have been the fish.
Excuse me?
It was the fish.
It was the fish, but it did for 10 years.